spectroscopy. So just to summarize, we went over the spectrometers. We looked at the infrared spectrometer, talked about the interferometer. We talked about the ATR and the trampoline and the guy's legs, and the molecules' vibrations can steal some of the light. Even though the light doesn't actually leave the diamond, at that interface they can interact. We talked about Raman spectroscopy and how the laser light hits the molecule and shakes the electron cloud, and there's a chance that the vibrational motion can steal some of that energy too and scatter that photon with less energy. So the missing energy went into the vibrations. So there's lots of things that can happen with vibrations and this electronic excitation. But Raman is really good because it gives us vibrational information using visible light. And then we got into assigning the peaks in the spectrum. We looked at the infrared spectrum, and every peak was a fundamental. And then we had a few peaks that were combination bands or overtones, and that's what we're going to talk about today. But before we got to this, we went around a little side trip to rotational spectroscopy to look at the rotational constant, and the bond lengths and the mass of the particles are in that rotational constant. And then we combined those in row vibrational spectroscopy, where we had the P, Q, and R branch in infrared. And what was the Raman one called? O, Q, and S. So it was O and S were Raman with the Q in the middle, and then P, Q, and R were the IR. So today we're going to kind of loop back to the regular vibrational spectrum, and we're going to hit the overtones and the combinations to kind of see where some of these other peaks come from in the infrared spectrum. So this is a automobile exhaust, and even in just a simple sample, you know, you're burning a hydrocarbon, you have CO2 and water, those are the main products. You have a little unburned hydrocarbon and the carbon monoxide. Super simple molecule, very easy signal to get, and that's what you guys are going to analyze to get that bond length. And then we had these extra peaks up here. They're obviously a gas phase peak because they have rotational structure. This right here, that lump right there, that's, who knows what that is. I mean, it's a little higher than the 3000 would be CH stretch. That's probably moisture on the windows of the cell. So again, we're sucking combustion gases out of that. Some of those combustion gases are water. We see the water band here. We see a little bit of the rotational structure of water there. But if you have condensation on the window, then you have liquid water. And so this little hump right here is probably liquid water on the surface of the cell. But this is not liquid. Those two bands are gas phase because you see the rotational structure. So it's a row vibrational structure, but we've already accounted for all of the vibrational modes in CO2. We have the bending motion, and that's doubly degenerate. So how many, first of all, let's back up. CO2 has 3 atoms. So how many total things can that molecule do in terms of its motions?
Like 9?
Yeah, so 3 times the number of atoms, because every atom independently can go in X, Y, and Z. If you bind them together, you restrict their motion in some way. So then all 3 atoms as a group can go in X, Y, and Z. That's translation. The whole group can rotate. Now, it's a linear molecule, so how many rotations does it have? Only 2 are defined. Rotation around the axis of the linear molecule is not defined because there's no mass off the axis. You can't tell it's rotating. So there's only 2 defined rotations for a linear molecule, around the x-axis or around the y-axis, so the tumbling motion. So there's only 2 rotations for a linear molecule. So if we take the 9 total motions, we subtract out the 3 translations, and we take out the 2 rotations, we have 4 left over. And those 4 are vibrations. So if it's not translation, not rotation, it has to be vibration. So that adds up to the 9, because every molecule, 3 times the number of atoms, that's how many things it can do in terms of its motions in space. Take out the rotations, take out the translations, and everything else has to be a vibration of the molecule, which means the center of mass stays still, and the atoms just move around the center of mass. Because if the center of mass moves, that's translation. It's going, the whole molecule is moving in X or Y or Z. Now, of course, in nature, these are happening at all the same time. Like the molecule is going crazy as it moves through space. But we, as mathematicians, physical chemists, we can separate each of those motions and say, let's just not let's just move our frame with the molecule as it goes through space so it doesn't look like it's moving, and then we can see the vibrations as it goes along. Now, of course, the CH stretch is really fast and the bending motion is really slow, and they're such different frequencies that we can separate those and we can talk about them independently. And so that's what's happening here. In this vibrational spectrum are the independent vibrations of the molecule. This one is doubly degenerate, and that's the bending motion. So that's the CO2 bending like this or like this. So it can bend towards the X axis or towards the Y axis. Yes? For symmetric molecules, it's a good question. So for the videos, you said, how do you know if it's doubly degenerate? Let me jump ahead to this acetonitrile motion, or this one here, right here. See all these vibrations? So you have A1s, vibrations of the molecule, and you have E's. So if the motion has an E symmetry, it's doubly degenerate. So that's one way to answer that. But how do we decide if it has E? We would look at that vibration in the arrows. And remember when we did for water, the arrow components that canceled and the ones that didn't, and we found the dipole moment change for that vibration? If that dipole moment change is on an E row of the character table, then it's doubly degenerate. So for CO2, it's a D infinity H character table. And if you look at X, Y, they're coupled together, and they're saying that X has the same energy as Y. Whenever you see those parentheses, and it would be on an E row. Okay, so that's how you would know. Now, for a symmetric molecule, all of the ones that are, if it's a symmetric molecule, the Z-axis is the axis of symmetry. So any motion 90 degrees to that is going to be doubly degenerate. So what did we mean by a symmetric molecule? Anything that has threefold symmetry or greater. So acetonitrile is a threefold molecule. It's C3V. So it would have degenerate motions in X and Y. So if the axis, so if I've got my CO2, so here's the carbon, here's the two oxygens, the axis of symmetry goes this way. It's the axis of the molecule, right? So the Z-axis goes like this, if this is the molecule. So motion in this direction would be X, and motion in this direction would be Y, or vice versa. And so those would be 90 degrees to the symmetry axis, and in a symmetric molecule, that would be doubly degenerate. Yeah. So that's how you would know. So you would draw the arrows of the motion compared to the character table and know that X and Y have the same energy. So back to this one. So we have CO2. It's, again, going to count for two of those vibrations. Then we have the asymmetric stretch. That's a third vibration. And then the Raman active mode, which we don't see on this spectrum, is the fourth vibration. So there's all four vibrations for CO2, but one of those is doubly degenerate. So we really only see 3 peaks, but the doubly degenerate one shows up there. Yes.
What were you pointing out about the combination bands at the end there?
Yes, and so we know that they're gas phase because there's some row vibrational lines. Like if it's liquid phase, then you can't get the rotational spectrum. They can't rotate because it's a liquid.
Okay, so after like the two big noticeable peaks, you're talking about the little part after that?
No, this hump is liquid water.
Okay.
And then this big mess right here is the 3684 combination band. And this little hump here with all those little peaks is the 3731. And then these little bitty humps right here are water. And the reason the water is so messy is because the spectrometer software is trying to cancel it out. So there's water in the background and there's water in the combustion, and so it's canceling out and it's making it look a little bit noisier than it should. But anyway, that's the water. So this combination band can be confusing because if you're looking at CO2 and you add them up, we've got 4 vibrations. I've got 1, 2 here for the degenerate mode, 3, okay, and then I know there's a Raman active mode, which is 4, and so this is related to CO2, but I'm out of vibrations. This would be 5 and 6, and the molecule doesn't have enough atoms to have 6 vibrations. And if one of those was degenerate, there'd be like 7. So this is a problem, right? If these are all fundamentals, I've run out of normal modes of vibration, and yet I've got peaks that are related to CO2. Now you may say, well, how do we know it's related to CO2? Let's put more CO2 in the cell and see what happens, and they would grow. with the CO2. So we would know, okay, this is related to CO2. We can change the concentration and see that they go up and down with these other peaks. So we've got to figure out what those are. And if you look in the literature, you find out that they're combination bands. They've been assigned to be combination bands. So let's talk about what those are. So these are the fundamental transitions, the normal modes of vibration for the CO stretches. You have the symmetric stretch, the lower one, which is 1388, and that's Raman active. You see, that's the A1G. And I've put these lines kind of, trying to do them to scale. So like this different distance here is, around 1400 wave numbers, and then the other one is 2350. So this one, is that layer, that one right there. This is this one right here. Notice the z-axis. It's along the axis of the molecule. And so we could do these two experiments and we could get those frequencies. But let's look at the combination bands. Here's the bending motion, the 700 wave number motion. So this one is right here. And notice how we're keeping track of these motions. We're calling them nu 1, nu 2, and nu 3. We're also showing the quantum numbers. Like the ground state is 0 in each of those quantum numbers. Nu 2 is that XY motion. It's doubly degenerate, and it's so you see I've put one quantum in the second vibrational mode, but the others are still 0. So this molecule here is only excited in that vibration shown here, but the others are not excited. Up here, this is nu 1, the Raman active mode. So it's 1, 0, 0. So these two vibrations are not excited, but this one is. And then that top one, nu 3, the infrared active mode, you see its quantum number, that right there. So that little serial number, that's each of the wave functions for those vibrations has got a little quantum in it. Okay. So we have the IR, the Raman active, and then we have the IR active, this bending motion. And then we have this combination band. Look at the quantum numbers for that one. You see it's one quantum excitation in nu 3 and 2 excitations in nu 2. And so we have symmetries associated with those. So you see it's this one here. This is the 001, and 2 of these. So this distance right here is about 700 wave numbers, and so it's meant to be 1400. So it's supposed to be 2 of those units right here going up. So it's this jump plus 2 more of these gives you this level right there, and that motion is IR active, that combination of those quantum states. So this is again a really strange result, because we have 2 wave functions that are being excited at the same time with 1 photon of light, but it's coming into the molecule, it's exciting that motion, and that's what we end up with. So let's look at the symmetries associated with those. So the way we'd write out the transition dipole moment integral is we would put all the quantum numbers, all the wave functions represented by their quantum numbers in there, and we would put light in there too. So this would be our transition dipole moment integral. So it gets a little more complicated. We're adding more and more quantum numbers into our transition dipole moment integral. I'm glad that we only did that for the particle in a box with just one wave function. Now this integral would be really messy. We'd have 7 functions multiplied by each other and integrated over all space.
Yeah, thank you.
Yeah, so that's a mess. I don't want to do that. Yeah, but you can put the symmetries in there and see if it works out. And so here's all of the symmetries for all of those wave functions. I have the E1U in there twice because we've excited that mode twice. Yes.
The quantum number, I think I'm getting confused with the quantum number and then putting it with the actual character table. Because I thought before we were going like directly to the character table and then figuring out if it was like even odd. Mm-hmm. And that's what those quantum numbers look like, but that's not what those are, right?
These quantum numbers aren't telling you, just the numbers themselves are not telling you anything about even or odd. Okay. You have to know the symmetry of the motion.
Yeah, it's just the like from 1, 2, or like wherever it's like jumping the excited state, like 1
Mhm.
to 2 fundamental, or is that what that is?
Yeah, so 0 to 1 would be the fundamental. And so this would be the fundamental for this motion here. It's the 0 to 1 in the first vibrational frequency. So the Greek character for the vibrational frequency is nu. So we would call that nu 1, meaning the first vibrational motion, not the first energy level. So the first vibrational motion is excited by 1 quantum. So we're excited in nu 1, but nu 2 and nu 3 are still in the ground state.
Gotcha. Okay.
Yeah, and then this one is nu 3. So nu 1 and nu 2 are still in the ground state, but nu 3 is excited. And then this one is the 2, nu 2 plus nu 3 combination band. So we've excited the second vibration twice and the third vibration once. And that's the energy of that, because it's the 2300 here plus 700 plus 700 again. So you add up all of those frequencies, 2 of the vibrational frequency number 2 and 1 of the vibrational frequency number 3, add all that together and you get the location of the combination band. Yeah, so that's, so, and it's not exact, but it's close. Like, you know, experiment. Yeah, so the vibrational frequencies in this new, you know, multi-excited molecule might be a little different than their pure vibrations, because they talk to each other. The spring constants, you think about all the springs talking to each other. If you had this molecule made out of springs, they would all interact, and that's what happens in the real molecule. Yeah. And so this is where we get those, what I just added up. The 2 times 700 plus 2300 gives you 3700, and that's pretty close to the 3684. Yeah. And so that's how they come up with that. They're like, we've got a motion at 3684. How do we get that number? And they could add up all of these. It's certainly not, it's not 1300 plus 2300. Let's see, that would be 26. That'd be 36. Well, it could be close to that. It could be like nu 1 and nu 3 would be close. Yeah. And so then they would do some sort of experiment to figure out which one of those that peak actually is. Yeah. So we can look at the symmetry support for that. And so here's our transition dipole moment integral, and we can put the symmetries in for all of those. Remember, for vibrational motion, the ground states are all A1G, and then they alternate in the excited states to the symmetry of the motion, then back to A1G. And so then we have light here, represented by this A1U from the character table. And then we have nu 3 for A1U. 2 times this motion gives us these 2 symmetries there. And then this one is still A1G because it's not excited at all. And so then we just go through the direct product table. And these are pretty easy because all the A1Gs, anything, A1G times anything gives itself back, right? So all of those would give you A1G. Yeah, exactly. And then you have the A1U times A1G. The U and the G gives you U. And then we do that again. Now we have U times U, and that gives G. And now finally things get interesting. We have E1U times A1G, so that would be E1U again. And then we have the E1U times E1U. So we would look at the direct product table, and we see that anytime you have E times E, E1 times E1, you get to A1, A2, and E1. And then the U times U gives you G. And then we take this times each one of those. So A1G times A1G gives A1G. A1G times A2G gives A2G. A1G times E1G gives E1G. So it's just, you know, the A1G times everything will give it back. So here we are at the end where we have no more things multiplied by each other. We just have things added to each other.
Isn't the third line just proving that the A1U times A1G is A1U? That's not A1U.
Where's this?
On the third line.
This one here?
Yeah.
So it's the U times U that gives you the G.
Wait, but right, okay, so then right above that, the A1U times A1G is not A1G.
No, because it's the U times G. So think of the U's as -1s and the G's as +1s. And so this would be a -1 times a +1. And that's going to equal a -1. So that's going to be a U.
Okay.
Yeah. And then here we have a -1 times a -1, which gives us a +1.
Okay.
Yeah. So that's a way to think of U's and G's, is the plus ones and minus ones.
I was just seeing that doesn't anything times itself also kind of usually go back down to the ground state.
Anything times itself will give an A1, and then you have to look at the So like this, it will contain it. So like here's E1U times itself, right? Now the E's give you all three of these pieces, okay? And it's nice because the vectors actually work out. The E's are doubly degenerate. So if I say something that is worth 2 and another thing that's worth 2, multiply, I should get 4. Okay, what do I end up with? I get a singly degenerate A and another singly degenerate A and a doubly degenerate E. That adds up to 4. Yeah, so I end up with 4 things out of it. If I take 2 times 2, I end up with 4. One's an A, and the other is an E, and that adds up. So this is all, I mean, I'm not teaching you the math behind all of these, all the vectors and everything, but it's those rows in the character table. If you were to multiply every element in those rows, you'd get a bunch of numbers, and then you could decompose it into these elements. And the, it's all of the numbers are conserved. You're not going to like gain or lose degrees of freedom. Yeah. So here we are. Then this integral down at the bottom has a lot of odd terms, but there's one even term in it, and that even term will be non-zero. So this combination band is allowed. Let's say you thought this was some other kind of combination that added up to 3600, and you looked at the symmetry and it wasn't allowed. Then you would know it was not that one. So the symmetry could give you a handle on these combination bands to figure out if this is actually allowed or not. So that's how you would do it. And so then let's look at these normal modes and frequencies of acetonitrile. This was one of the spectra I showed in class like 2 or 3 lectures ago. And here we had all of these different peaks that were assigned. And I kind of skirted past these that had nu3 plus nu4 and so on, because those are combination bands. So here's a combination band. And here's one, nu7 and nu8. And we've talked about overtones in this class. Well, there's an overtone. So 2 times nu8. So nu8 is a really low frequency motion. It's around, in the 300s. Let's go back and look at the vibrational motions here. Let's see. Nu8. Yeah, down here, 360. So it's beyond where our regular mid-infrared stops around 400 wave numbers, but when we use KBR windows, which we have in our spectrometer, it really stops at around 500. It's still noisy until 600, so we just chop the spectrum off at 600 wave numbers, and so we would never see nu8 in acetonitrile. So how do we know what this spectral value is? Well, we could go to the far infrared and get it, or we could look at the overtone, and the overtone should be about twice that number. And so we would be able to calculate that value for nu8 if we saw the overtone, and sure enough, there it is, this 2 nu8. Yeah, and so we could take that frequency and divide it by 2, and we can get a value for what that nu8 is, even though we can't see down that far in the infrared. So that's a really good use of it. And then here's another value, a measurement of nu8, where we have this combination band of nu7 plus nu8. So we could get a measurement for nu8 using this overtone and using this combination band. So there's 2 values that we could use to determine the frequency of that 8th vibrational motion, even though we can't see it directly in this spectrum.
You're saying with that combination band, we would just use whatever values here for that is actually.
Yeah, so here's nu7 right here.
Okay.
And so, and so we could say this right here minus nu7 by itself. Oops, that looks like a Z. Minus the frequency of nu7 would equal nu8. Yeah, so that'd be a pretty slick way to do it. So let's look at some of the symmetries of these combination bands. So here's the nu3, nu4 combination band. We're leaving off, since this has 8 vibrational motions, we would have 8 quantum numbers in the transition dipole moment integral. But a lot of those are 0 on both sides, and so they're going to be A1 on both sides. And so we'll just skip all of those. But yeah, the integral would have 8 vibrational functions multiplied by each other, light, and another 8 vibrational motions. But if those are even, then on both sides, they don't impact the problem at all. So we're just going to look at the changes between nu 3 and nu 4. So they go from 0 to 1 in both of those cases. So if we look at nu 3 and nu 4, they're all A1s. So this is an easy one. It's even times even times even all the way across. So I went ahead and show the whole progression. But yeah, this one's going to be non-zero because this is a vibrational motion that goes along the axis. It's parallel to the symmetry axis. Okay, let's look at the next one. It's a little more interesting. Nu 7 and nu 8. Okay, the symmetry of nu 7 and nu 8 are both E, so they're perpendicular to the symmetry axis. And so let's look at this one. Notice there's no G's and U's. Review question, why? Pardon? Nope. I just didn't hear you. Someone else.
Is it because the harmonics make it even if it's supposed to be odd?
No, let's look at the molecule. So this is acetonitrile. So this is the nitrile piece. Okay. Acetate, right, that's 2 carbons. So here's the methyl group on the end. You see the C threefold symmetry? Okay. Where's the Z-axis? Up and down, yeah. So this is the Z-axis. Coming out of the board is the, which one? Look, your right-hand rule. And this one's 90 degrees to that. What's coming out of the board? X, yeah, X, and then Y. Okay. So why does this one not have G's and U's in its character table? What is the G and U tied to in the character table? What column? So there's the columns are the symmetry elements like E, a C, a sigma, an I, and an S. Those are the 5 symmetry elements. So identity, rotation, reflection, inversion, and improper rotation for rotation reflection. So G is associated with one of those columns. Inversion. Now, a molecule doesn't have an inversion column if it doesn't have an inversion center. Those columns are every symmetry element that molecule possesses. So this molecule possesses a C3 axis, and it possesses 3 sigma planes, but it doesn't possess an inversion. It doesn't possess an improper rotation. So yeah, it doesn't possess any C2s. It's got 1 C3 axis, but no perpendicular C2s. No sigma H, because its top doesn't look like the bottom. So this is just a C3V molecule. Can you look at this molecule and see that it's very similar to ammonia? Yeah, so you can just, the top of the molecule in ammonia is just the lone pair. And so this would be the classic example of a C3V molecule. And if I know that ammonia is C3V and I look at acetonitrile, yeah, it looks the same symmetry. It's a different molecule, but the same symmetry. Yeah. Let's yes, that's good. Okay, so C3V only has A1, A2, and E in terms of its rows. And so there's no G's and U's because it doesn't have an inversion center. So that really simplifies things. So we'll just work our way through. A1 is A1. Do that again. And then we have E, because A1 times E is E. And now we get to the E times E. So we go back up here to the direct product table. E times E is the same kind of thing. A1, A2, and E. And we have A1 as one of those last pieces. So this is not equal to 0, so that's allowed by symmetry. Whenever you're doing this in your problems and so on, keep the brackets. So this is, again, those brackets mean integral over all space. Dirac notation. Integral over all space. And so these are the integrals over all of the vibrational motions and everything. So it's fantastic. Okay, then the new 7 new 8 combination band. This one is, so this was the last one we did with 7 and 8. We did with Z polarized light, which was the A1. Let's do it with X or Y polarized light. So same problem, but now we have XY polarized light. And I only include this one because I want you to see what happens when we have 3 E's in the problem. Okay, so the first part of the problem is very similar, A1 times A1, and then we have A1 times E, but now we have 3 E's. So the first 2 are easy, A1, A2, and E, but then the next one is all of these. So let's see where these end up. So this is E times A1 gives E, so it's over here. Okay, E times A2 gives E, so it's over here. So that's where 2 of these E's came from. And then E times E gives A1 times A2 times E. So that's why we have 3 E's. But we have the A1 and the A2 from that last combination. And so we end up with, again, an allowed transition. So this one is allowed by all 3 motions, or light, X, Y light, or Z light. Okay. Let's go to questions. And then if there are no questions, we can do a Kahoot. But I want to make sure that you guys get a chance to ask your questions. Yes? 18. Okay, so look at the figure up above. What's the designation for the 2821 wave 0.5 wave number peak? 2821. So where are we? Right here, 2821.5. So this one right here. Okay. So first of all, we've got, what is this? This is what kind of spectrum? What? Yeah, so, but it's a row vibrational spectrum. And so we have P and R branches. Yeah, P and R branches. So this is the high side, right? So this is R. Yep. And so this is P. Okay. Now, notice I'm talking about, at least in these first 2 problems, 37, H37 HCl. Okay. Now, let's say it's been a long time since you took Gen Chem, and you can't remember which is the most abundant isotope for chlorine. How would you figure that out? It's relative abundance, but look at the periodic table. What is the average mass of chlorine? Not quite 35. 35.5 roughly. Yeah, 35 and a half. And so that means if I've got 2 possibilities, I've got chlorine 37 and chlorine 35. Okay, these are the isotopic masses. This is closer to that one. So that means the 35th, the isotope with mass 35 is the more abundant one by about a 3-to-1 ratio. Okay, so that means these taller peaks are the chlorine 35 isotope, and the smaller peaks are the 37. So that's the first 2, 16 and 17, are asking that question. But that's how you would figure it out, even if you didn't have memorized what the isotopic abundance for chlorine is. You could look at the periodic table and go, oh, what's the most abundant one? Let's do boron, just for grants. Boron has 2 isotopes, 10 and 11. And what is the average mass? I know you can't see that. It says 10.8. So what do you think is more abundant? Boron 10 or boron 11? 11. What percentage roughly is it? It's about 80% boron 11 and 20% boron 10. That one's easy to do because they're just 1 unit apart. You know?
So you can just do like 100%.
Yeah, that's right. Those are the easy ones. Yeah. I think bromine is like 79 and 81, and it's 79.9, so it's about close to 50-50. 79 and 81, but don't quote me. I haven't looked at that one in a long time. There's some fluorine isotopes. That's easy when there's only 2 major isotopes. It gets real tricky when there's 3. And so but anyway, that's So let's look at this. Use the figure above. What's the designation of this 2821 peak? So we know the R branch and the P branch. What are the first two peaks closest to the missing Q branch?
R1 and P0.
Yeah. You got it backwards.
What? I do?
Yeah, it's R0
P1.
and P1. Yeah, I was about to say yes, but no. This pair is R0. And why do I say the pair? Well, because it's R0 for one isotope and R0 for the other isotope. Okay, and this pair here is P1. So then this is P2 and this is P3. I'm running out of space with the screen. Okay, so that's going to be P3, and it's the taller peak, so it's the 35. So it should be this one. Did I get it? Yeah. So those are all the different thoughts that you need to think about to answer that question. Yes.
And so, like, the one to the left of R0, that would be like R1?
Yes. So then we go to the left. So this is this one is R1. This tallest one is R2. This one's R3 right here. And this one's R4. We need to come up with a row vibrational spectrum of row vibrational spectrum. It had to be Raman because it's a symmetric molecule for deuterium, D2. And then you would have a R2 D2. Because you had the second R line for not dihydrogen, but deuterium, dideuterium. So R2D2. That would be sweet. I got to figure out how to work that in. So, good. Okay, so let's see. The rotational constant. So then use the R0 and R1 lines. I have to tell you which ones to use because I want your number to match my number. And so we have the 0 and 1 lines for 37. So that would be the smaller ones for these two right here. Okay, so that's 28, 23.7 minus 29.04.1. That's 29, not 28. I can't read. 0.1. Okay, so this is 6, 13 minus 4. Was that 9? Okay, 1. Okay, 19.6. And what do I need to do to that number? Divide by 2, exactly, because that's Hamlet, right? This is IR, 2B or not 2B. This is 2B because it's IR. Okay, so what do I get? 9.8. Raman was 4, yeah. So these are all wave numbers. But see, there's no unit on this guy, so that's why I emphasized that. You know, you might take the difference and think, oh yeah, the rotational constant is 19.6, but that doesn't work because that would be way too big for this molecule. So it's 9.8 wave numbers. What other questions?
How do you do
16. See, R and P. Yeah, okay, so this missing Q is going to be exactly in the middle of those lines.
You just take the two small ones, divide in half, and add one of them?
Exactly, yeah, that's right. Yeah. And so, and that's what you're going to see in your lab because we're going to define this running quantum number. So for the P1 line, it's going to be -1, -2, -3. For all of the P lines, it's just -J. And for the R lines, it's J plus 1. So this 0 would be 1, and the 2 and the 1 would be 2, and the 2 would be 3. And so you see where 0 is? 0 is right in the middle. And so when you do, when you plot those frequencies versus M, let's see. When you plot those frequencies versus M is right here in a 0, where M crosses 0, you would have this y-intercept where M equals 0 would be the vibrational frequency. So you could just average those is another way to do it, essentially what you're saying. So for 37, and so that's these smaller ones. So you would take the average of these two numbers and it would be right there in the middle, and that would be the vibrational frequency. So it's a very accurate measurement because you could also average the next two and the next two and the next two, and you could get a really good number with a good standard deviation. And that's what your regression is doing. You're going to plot all of these frequencies versus those M numbers, and when you do a regression, it's like getting 50 different averages for that same number, and you'll get a really good statistic on it. In fact, that one in particular, I looked at the spreadsheet, and you're able to determine with 7 significant figures. So that's really good.
Just to make sure I understand, we're using the smaller peak because the less abundant 37. Like
Yes.
if it was 35, then we would use the higher.
Yes,
Okay.
yes. And I did that just to make you guys figure out which particular peaks am I using. Now, this spectrum is this is a great spectrum, and it would be great to analyze, but it's out there a lot, and so I went ahead and have y'all. I'll talk about the HCl spectrum in class, but then in lab y'all do carbon monoxide. Yeah. Yes.
You do 22 or 23.
Oh yeah. So these are the overtones. Very good. So if we're going from 0 to 2, it's roughly twice that frequency. Okay, so if this is the vibrational frequency, the first overtone, so here's your vibrational frequency, the fundamental would be 0 to 1. So 0 to 2 would be 2 units of that. So this is the spacing between these energy levels. And so you'd have 2 of those spacings. So you just multiply that by 2. And so that gives you the 5760, I think, unless it's none of the above. I don't know.
And then 23 would just be the same number then? Because it would be multiplied by 1.
The first hot band would just be 2880. Yeah.
Okay.
Yeah. And again, there might be a slight change for anharmonicity, but I don't, it says, it doesn't say neglect anharmonicity, but the first estimate would be just 2880. Because that would be the hot band, the first hot band would be this one right there. Can you see that? It's kind of small. Yeah.
Could you go to 21?
Yes.
I didn't understand what it was asking.
Oh, yeah. So this is the relative standard deviation. Okay, so that would be the uncertainty in the rotational constant over the rotational constant is equal to 20. Okay. So this is the standard deviation. So go watch that propagation of uncertainty video where it talks about how to manage these things. So the RSD, so if we have y equals mx, right? So the RSD in y is equal to the sums, the square root of the sums of the RSD of m squared plus RSD of x squared. Another way to write that is the RSD of y squared is equal to the sums of all the RSD components that goes into it. And the relative standard deviation is just that uncertainty over the value. X squared. Okay.
When are the squares be canceled?
Not because of this addition. So you square each individual term. I don't really need these parentheses here. I need this parenthesis. I need this parenthesis out here, like this. So you square individual terms, add them together, and then take the square root, and you get the result. Yeah. If they were multiplied, you could cancel them. So go to that propagation of uncertainty video. This one is pretty straightforward. So we have the bond length. We're out of time, but it's in that propagation of uncertainty video of how to do this one. And that'll prepare you for the lab.